now. Yeah.
Okay, so thank you all for coming. I've given variations on this talk a couple of times over the last week. So if you've seen them, I'll try to make it different by focusing on the bits that I didn't get time to talk through before. And I've deleted a lot of the bits that I spent a lot of time talking about in those previous iterations. If you haven't, then the bits that I deleted are mostly fairly straightforward disease modeling stuff that I guess many of you will know anyway. So this is joint work between myself and David Kavanagh, who is on the line somewhere, and he's CEO or chief something or other of Integrated Energy.
Director.
Yeah.
Thanks, Michael.
Who are a consulting company here in Perth, and David approached me and asked about what we can do about coronavirus, or about modelling it at least. And I'd been kind of thinking about it for a while, wondering whether there was, well, honestly, rather wondering whether there was any point in modelling it, because most of what was happening was exactly what standard models would predict, and at least in Australia, the government seemed to be listening to the advice they were getting from other modelers, so there seemed to be no need to do any more. David convinced me to play with it anyway, and so that's what we've got here today. So first things first, I have to get control of my screen. So this is kind of standard perceived wisdom of how to model disease dynamics. This is exactly how you would teach it in second year undergraduate mathematics, dynamical systems. You have a susceptible pool. Usually there'll be an exposed pool as well, but we're just going to have susceptible, infected, and removed, so S, I, and R, and essentially just rates of transmission between susceptible to infected, the RSI term, and infected to removed, the AI term. The important thing to note, okay, so first of all, there's two rate parameters, R and A. Second thing to note is that the rate at which people get the disease is the product SI. So that means it's the product of contact between susceptibles and infected. And it's assuming that all of the susceptibles and all of the infected individuals are kind of lined up and mix up with each other and infect each other at some constant rate. So it's assuming a homogeneous population and mixing of that population. So it's assuming perfect mixing of everyone in the population. The other thing to kind of notice is when you apply this to actual data, which is what I've got on the right here, this is number of, well, the bottom plot down here is a proxy for the daily value of infected IT, so the current number of infected individuals in the population for the SARS coronavirus in Hong Kong in 2003. So this data is 17 years old, but it's a coronavirus nonetheless. And from that, we can deduce the number of people in hospital, or in fact, that's the data that we've got. And we can also divide it up by different districts. So here we have all of the districts of Hong Kong. Essentially, Hong Kong's divided into 3 different regions. There's an island, Hong Kong Island, and there's 4 regions on the island. They're the red ones here. For Thomas, that's the reddish grey lines here, here, and here, and here. Across the harbour from Hong Kong is Kowloon, which is the tip of the peninsula, and those are the yellow ones. Kowloon City, Yau Tsim Mong, Sham Shui Po, Kwang Tung, and Wong Tai Sin. And then you have the green areas, which are the kind of next piece up. It's away from the dense urban part of the peninsula towards the border with China. So all of these districts are arranged together. And the thing that I want you to note from this is that if you look at the way the number of inpatients are appearing across the districts, is there's some variation from district to district, right? It's not uniform. There's some spatial distribution of how people catching, in this case, SARS coronavirus in version 1. So the usual way to extend this kind of SIR, ordinary differential equation model, would be to include diffusion. So you could imagine disease diffusing from areas where there's an earlier wave front to ones where it's later, and that would capture a lot of the features here. But diffusion doesn't really work when people are moving around large distances in a more of a long tail distribution in terms of people's movement patterns. So diffusion, and also when there's relatively small numbers of cases, the outbreaks depend on individual movements rather than an average. And that comes out in the plot down the bottom for infected as well. It's rather bumpy, and it depends on specific unusual events rather than a nice smooth average, which you'd get from solving these equations. Okay, so that would kind of motivate us to think about networks, because we are always thinking about networks, and to think about contact patterns amongst people as the network, and disease transmission being spread between nodes that are connected on that network. So essentially, every node in this network is an individual, and we are mapping out all the contacts they have with other individuals and saying that they can only infect other individuals with whom they have a contact. Everyone starts out being susceptible. Well, that's pretty boring. Someone's got to be exposed. Everyone starts out being susceptible, apart from a small number of exposed individuals. Those exposed individuals become infectious, they infect their neighbors, and so on and so on. The only caveat here is I have to admit this isn't actually a contact graph for transmission of a disease. This is actually, well, I guess mathematics is kind of a disease. This is actually contact graph for transmission of mathematics. Every node on this graph is an Australian mathematician or co-author of an Australian mathematician, and the contacts is if they wrote a paper together. But the same idea holds. A whole range of different social networks have the same type of structure of connection. And so the idea is that we're going to take this kind of statistical description of the structure, that is the degree distribution, translate it over to agent-based model for disease modeling, and ask questions of how the disease spreads on the network. And then the interesting part for coronavirus is, because various places around the world have different control measures, these control measures are not just fiddling with the rate R and the rate A. These control measures are actually changing the structure of the network. So that's what we intend to model. So you can think of it, the general model, and this was work done in 2006 for the 2003 SARS, but same basic idea applies here with just different models. Susceptible, exposed, infected, and removed. Transition between susceptible to exposed to infected to removed. We've got two rate parameters for transmission between E to I and I to R. And well, in this model, we had two rates of infection, depending on whether we had a close connection on the lattice here. We're modeling everything on a lattice in this case, or long-range connections. So the model that we used for SARS 2003 was connections on a lattice, regular 2D grid, with periodic boundary conditions. So that gives you the torus here. And then on top of that, I better turn that off, otherwise Dave's going to get upset. We've got a torus, local connections on the torus, and then we're going to have a few small number of long-range connections between remote sites on that torus. And so that effectively turns this large network with a large diameter into a scrunched up copy of itself with a very small diameter because of these long-range connections. So we get, if you look at the diagram of dots in the top right, we get diffusion through neighbors on the lattice, and we get these jumps to new sites of infection and spread in the new sites of infection. In addition, to make this model of SARS from 2003 work, this is a bit of a kludge that I'm not going to use in the 2021. To make this 2003 model work, we essentially enforced a scale-free distribution on these long-range connections. Okay, so that's the basic idea. We can do that, we can simulate that. We see clusters of outbreaks, we see the bursty behavior, we see the large outbreaks due to the scale-free network, and the data and the time series that the model produces looks like the time series that we observed in Hong Kong at the very start. But there's still an open question, at least there was an open question, as to whether or not contact patterns really look like scale-free networks. Is it really the case that you get a small number of people with a large number of connections? And because if so, that's going to have a very great effect on the way the disease is spread. So this is now fast forward from 2003 SARS to the bird flu outbreak in Hong Kong and around the world subsequent to that. And what we did was take data here of all of the cases of bird flu here this is basically East Asia. Every dot is a reported case of avian influenza in a bird. These can be wild birds or poultry farms or whatever. These are reported to a international body. It's the animal version of the World Health Organization. I've forgotten the acronym, but they've got all the data. And we then join up connections between these outbreaks if we figure it's likely that a bird could get from one place to the other. So you've got this spatial temporal time series of locations of outbreaks, and we are then creating a network where each outbreak is a node on the network, and we're connecting cases where we can see a bird could have got from place A to place B after getting infected and before dropping dead. That gives us a network. It's more complicated than the three clusters you can see here because it actually goes over several years. So it's a spatial temporal network, and it's sort of bouncing back between East Asia and Europe and back again. We can look at the degree distribution on that network, and that's what's plotted in the bottom picture here. And when we do that, surprise, surprise, because I'm talking about it, the degree distribution follows a power law. That is, the probability of a node having degree k scales on a log-log scale like at least a fat red line, if the red line's fat enough. And indeed, the exponent of this is quite small, so it's quite a flat scale-free distribution, meaning there's quite a high probability of outbreaks having a very large number of secondary cases. Now, this is important for what's going to follow when we talk about super spreaders and coronaviruses, and it's important for modeling of diseases on networks because there's a lot of literature in the community, in the physics community, where people have looked at disease spread on networks and shown that if you have a distribution like this with a power law, a long tail in the number of connections that your nodes have, then when you look at the number of secondary cases, that's R0 or RF, EFF, the effective reproduction number, then because there's a probability that you're going to that an infected node is going to have an arbitrarily large number of neighbors, whatever value of infectivity and removal you have, the disease is going to spread. Because as long as there's infection, once you get to that node with very high degree, it's going to infect many, many more secondary cases than you can deal with. So the tail of the scale-free distribution means that the threshold for an epidemic being endemic is now that R0 is 0, right? So any value of R0, any value of the reproduction number will lead to an outbreak if the outbreak is on a scale-free network, which is kind of bad news if disease is actually transmitting on these sorts of networks. So a potted history of the early literature on this. What I just described is the Passasaurus Vespignani paper from PRL from 2001, which was exactly a statement of that. If you have SIS dynamics on a scale-free network, then the threshold for an endemic epidemic is 0. We then took that and then said, which is rather obvious actually, if you truncate that power law, then you get a positive value of R0 and there's a chance of containing the outbreak. So the key message there is that if you have an epidemic spreading through super spreader events, large numbers of secondary cases, then the disease will continue to spread. The way to stop it spreading is to limit opportunity for these super spreader events, to limit the large number of secondary cases. And so effectively what that's doing, effectively what this paper in PRE is saying is that if we limit the number of people that can be infected from a primary infection, then that makes the disease a lot easier to control. Okay. And so that was also the message in this paper with Dave Walker, where we are looking at the super spreader events that occurred in SARS in Hong Kong. And we are finding that those super spreader events can be explained entirely through a disease with a scale-free distribution of contacts. Right, so another way of saying that is that in Hong Kong, in SARS in 2003, it's a different but related virus, SARS 2003, we saw individual cases which were labeled super spreaders because there was a large number of secondary infections. In fact, the medical literature had this stupid definition for super spreaders. They said a super spreader was an event that infects more than expected number of people. If a mathematician reads that, or a statistician reads that, that's just saying that anything that infects more than the mean is a super spreader. So not all epidemics have what I and now most other people think of as super spreaders. Super spreaders are events in the tail of a distribution. They're events with low probability, but have a high number of subsequent infections. So it's much better to think about super spreaders as being the events in the tail of a power law distribution. Sounds a bit circular now that I've said it like that, but it's not really. If you allow for individuals to have an arbitrarily large number of contacts, then you will get these bursts that match the data that we saw in Hong Kong in 2003. So the super spreaders, essentially we can explain them with contact patterns of people. Think back to the graph with the mathematicians with their contacts. So the highly connected mathematicians are the ones causing the disease to spread. We can explain what's going on through that rather than needing to resort to a more complicated explanation in terms of, in some people, the disease is more infectious or something else. Right? So the physiological explanation that is actually variation in the effect of the disease, I'm not saying that doesn't happen, but that more complicated explanation is not needed to explain what we see in the data. Okay, so that's 2003. We thought we'd dealt with it. We thought we'd got through that. SARS was over. It only infected a couple of thousand people, only killed 300, so everything was good. Almost everything was good. And then 2020, basically the same thing has happened again. This is two time series here. The slightly reddish orange one is the time series of infections reported for SARS in 2003 in Hong Kong. Normalized, well, there's no normalization. The vertical axis is absolute number of infections. The horizontal axis is date starting from January 21. So we start the two time series on the same date, just 17 years apart. Well, 17 years and 1 day because we've got a leap year to worry about as well. The blue line is the same measurement, new infections of SARS in Hong Kong in 2020. So you can see a peak pretty much about the same sort of time, and growth pattern, it's pretty noisy data, but it kind of goes up at about the same shape and goes down at about the same shape. So in many ways, we're seeing a similar sort of impact in Hong Kong in 2020 as we were in 2003. So the question is, if I showed just this data, well, in fact, you might actually be tempted to say that 2003 was worse than 2020, right? The graph for 2020 is actually lower. So what are we all worried about? Well, this is just Hong Kong, obviously. The rest of the world has not necessarily fared quite so well as Hong Kong has in 2020. But the question really is, why is that? What is the fact that drives this coronavirus to be so much worse than the other one? And there is a lot of work in physiology and the epidemiological literature exploring that, and a lot of really valid reasons why this one is more infectious, why this one is affecting more people, why the virus gets effectively stuck in people's throats, and there's a long latency period, and a whole lot of other things that drive this one to be worse than the other one. But I'm going to seek an explanation just in terms of super spreader events. So here's my model. Pretty standard stuff. Susceptibles, exposed, E, infected, I, and removed, R. And we transition from, first of all, from E to I and I to R with rates Q and R. So there's just if you're exposed, then there's some probability every day that you become infectious. That's probability Q. If you're infectious, there's some probability R that you become removed. Now, the only clever part is that if you're susceptible, there's some probability P that you become exposed only if, this is the Aij equals 1, only if you are connected to someone who is infectious. Okay, so there is, in addition to a state of every node, there is an adjacency matrix, and it's the connections on the adjacency matrix which determine whether the disease spreads from susceptible, whether an individual becomes exposed through contact with an infected person. Okay. And so the question then is just, well, what are we going to use for this matrix A, this adjacency matrix? And let me just fast forward so I can remember why I'm saying this. Initially, I'm going to use 4 different graphs. For the purposes of notation, I've labeled them as B and L with different parameter S. But essentially, I'm going to either say that contact follows a power law. So there's a degree distribution which is unbounded. Nodes have arbitrary large degrees with vanishing but not 0 probability. A very small probability, very large number of infections. All of these graphs, each of these different types of graphs has the same mean degree. Right? So I build the graph in such a way that every node, well, on average, a node will have 4 edges. It's just that on the scale-free network, although on average it's got 4, there's some with a lot more than 4. It's a finite graph, it's not infinite. A regular lattice, that's just the torus that I showed you before. It's 2-dimensional periodic boundary conditions. Every node has 4 neighbors. Random graph, that's, I'm going to take essentially an Erdos-Rene random graph. So what I'm doing here is I take my population of nodes and I assign link edges to random pairs of those nodes with some probability. And I do that in such a way that the mean degree is the same as number 1 and number 2. Finally, case 4, I'm going to start with a lattice, that's the donut, the torus again, and I'm going to rewire edges with some probability S. I'm not going to make this graph into a scale-free graph. I'm going to keep the mean degree 4, and I'm only going to rewire edges. I'm only going to move edges about. I'm not going to add edges. So the mean degree is going to be 4. Every time I rewire an edge, one node's going to gain an edge and one node's going to lose an edge. Why would I do all of this? Okay, so starting with 1, with the scale-free network, this is a model of business as usual. This is a model of everyone contacting everyone else as they would if we didn't have a pandemic on our hands. So people go to the football and they touch dirty surfaces next to the bar at Optus Stadium and they infect 500 other people. That's scale-free network. So there's a small chance of large outbreaks. And there's plenty of examples of these sorts of large outbreaks for coronavirus, right? There's football games, there's religious events. In a couple of months, we're going to have Donald Trump and his political rallies doing the same thing all over again. There's lots of examples. The lattice model, this is just saying everyone sit at home and only have contact with your neighbors in the sense of people close to you and people close to the people close to you. It's a bit of a kludge and a bit of an approximation because it's a regular lattice. So you have infection within households and between households at the same rate. But if that bothers you a bit, remember that you're going to the same supermarket as your neighbours. The key difference, however, is that because the disease is only spreading to neighbours, it's only spreading locally, and it's approximate, and it is spreading in the model as a diffusion process. Right? So you get this growth of a local cluster of cases. The random graph model, well, that's essentially we can go and move about and mix up with each other, but we're also going to be very careful about ensuring that we avoid large gatherings of any magnitude. Okay? So essentially, we still have a relatively small number of connections. We have a graph whose degree distribution is bounded. Finally, the small world lattice. Well, this is a model of imperfect work from home, imperfect isolation. What this is saying is that everyone is sitting at home only infecting their neighbours, just like the lattice model, except there's some probability that people aren't. And Thomas gets on the bike and cycles 100 kilometres somewhere else and has a beer with a mate down in Kalamunda and then drives back again. He's violated this local lattice and created a long-range connection. Okay, so those are the four models. We're going to model case 1, scale-free network, business as usual, full spreading. Case 2, full constraint, everyone in lockdown, just talking to your neighbours, and the only one spreading factors spreading between households is the postman. Random graph, where we are mixing, but we're avoiding any sort of large gatherings, and a small world lattice, where we let Thomas get on his bike and break quarantine every so often. Okay, so before showing you the results, I guess the key thing to think about is a little bit of what the effect of these network structures are on the actual disease dynamics. So the first thing we need to do is we take those SEIR equations and we create new equations where we now have got S sub k, E sub k, I sub k, and R sub k. So that is the number of susceptible nodes of degree k, exposed of degree k. The reason for this is if I'm a susceptible node of degree k, with k neighbours, and I become exposed, I become an exposed node of degree k, and then infected of degree k, and then removed of degree k, right? And that can be the same for every degree. However, a susceptible node of degree k can be infected by a node of any other degree. Here, that any other degree is the sum over the contacts between degree k nodes and infected nodes of degree L. So here, this first term, this is the rate of susceptibles becoming exposed, and there's that rate parameter P. If it's a loss of susceptibles, minus, that's a susceptible pool in contact with other nodes of other degree, depending on how many there are and whether or not they're connected. So PL is the probability of a neighbour having degree L. Okay, just a short comment for those that have seen this all before. Really, we want to have a conditional probability here. That is the probability of a neighbour having degree L, given that I've got degree K. That just gets a bit too complicated, so we don't do that. But the key thing then that we want to look at in terms of rate of growth of the disease is this term, this PKSK sum over the PL IL. So the infection of a node of degree K through its contact with other nodes of other degree. Okay, and we want to consider the 4 different network structures: scale-free network, that's B, the lattice L0, the Erdos-Rennet graph L1, and a small world network somewhere in between. So I've already claimed, and I'll show in a moment, that in case 2, L0, the lattice, we're going to have spatial diffusion. And the easy way to think about that is you've got that torus, you've got a point that's infected, it can only infect its neighbours, and they can only infect their neighbours, and so on, in a little circle growing around that infection site. And that circle is spatially propagating. L1, we've got random connections between individuals, and essentially, I'm claiming this is like homogeneous mixing, but essentially you're infecting 4 random people who infect 4 random people who infect 4 random people. Essentially what's going to happen is in this case 3, we can actually retrieve the original equations, and I'll show you that in a moment. In case 1, well, remember that we've got a degree distribution that gives a finite probability of an arbitrary large degree. And this means that we're going to get these big bursty events. It's going to be at least exponential because we've got mixing as we do with the case 3, but in fact, you're going to get these bursts that exceed exponential growth when you hit upon one of these highly connected individuals. Finally, I'll talk a bit more about the small world case and argue that it's a combination of 2 and 3. So let's start with the lattice case. We'll start with a lattice of where S equals 1. So remember, S equals 1 is this case that I'm claiming is homogeneous mixing, so that's just an Erdos-Rene graph. There's a couple of ways of rewiring it. So this is not the way I described it, but never mind. So I described it as an Erdos-Rene graph where I'm going to randomly assign links, and that will give you things where different nodes have different degree. An alternative is that you take every node, and this is what I'm arguing, this is what I'm modeling here. You take every node and you keep it with exactly 4 edges, but you rewire them completely randomly. Right, this is called the configuration model as opposed to the Erdos-Rene model. And I just realized that's what I'm saying here. So with the configuration model, the degree distribution is essentially everything has degree 4 and 0 otherwise. And so that rate equation just becomes our friend P times S times I with an extra constant. Right? Because the only term in all that sequence of compartmental equations of different degrees, anyone that has anything that's not 0 is degree 4. And so you're just left with the original sequence of equations. Configuration model, not Erdos-Rene model, as I just said earlier. So small error, but you can rewire. Yeah, the edge distribution is not, it's more complicated with Erdos-Rene one, but still going to give the same answer. Now, however, if we think about the lattice case, so now spread on the torus, we start with a single infected node and a single infected cluster. So all of the infected nodes are in one area. So we've got a cluster of all of the nodes that are either exposed, infected, or removed. So Lyle's just asked about why is it a torus. It doesn't have to be. I'm just assuming a spatially, so the critical thing that I want here is a spatially constrained lattice or spatially constrained structure so that you have connection to your neighbors. I chose a torus because I like donuts. It's easy to model. Everyone likes periodic boundary conditions, but the important thing is really the diffusion part. And all that's going to matter here, if you change it to a different spatially constrained structure, is you're going to get different diffusion rate depending on the dimension of that spatial constraint. One could argue, in fact, Lyle, that in Hong Kong, a 3-dimensional structure is probably more useful because you have neighbors vertically as well as horizontally. But anyway, your cluster is spatially constrained.
Topology, I wasn't thinking of the dimensions so much as the topology.
Yeah, so the topology, I'm sorry, the topology is not terribly important here. It doesn't matter if it's, what you do at the boundaries is not really important. If the disease falls off the boundary, then it's okay. It's only the bit that's in the middle that matters. You'll find this is a trick that physicists like to play. There's a whole bunch of work, I assume Shannon's listening somewhere, where people look at flocking models for flocks of birds, and they put them in a box and then assume that the box is periodic boundary conditions, just because it stops the birds from getting away. But I promise you, it's not terribly important feature of this model. The important feature is you've got a cluster, and that cluster consists of everything that's been exposed. And if it's 2-dimensional, then the boundary of the cluster is going to grow like something like the square root of that area, up to some constant. And so what you see then is that the contact between susceptibles and exposed is not, it's not what we had up here where all of the susceptibles and all of the infecteds are meeting and contacting, it's only at the boundary of that cluster. And so if we wave our hands a bit and apply a kind of rough counting argument, we've got a cluster of size E plus I plus R. The boundary of that is approximately scaling like the square root of that. I'm then also assuming that it's going slowly enough that everything interior is, all the removed nodes are interior, so the boundary just consists of infecteds and exposed, so some fraction of them are infected, and it's just contact on the boundary between the infected individuals, which have this number, and the susceptible individuals that have contact with them, which have that number. Square that, bit of normalization, and you get scaling of the rate of infection as something like this, right? So there's actually an infected term in the numerator and the denominator. So up to orders of magnitude, the rate of infection is your rate times just one parameter, one of the S, E, I, and R's. So it's almost linear in terms of infected, whereas this is quadratic. That's essentially the argument I'm making here. I'm waiting for you to argue with me, Lyle. No? Okay, I'll move on then. And so essentially the final piece of the puzzle is, well, we've got this type of growth if we are fully random connections, and it's just back to the original model. We've got this type of growth, we've got this type of growth if we're fully constrained on the lattice. If we allow short range connections with some probability, each of those long range connections with some probability, each of the times we have a rewiring and we hit one of those connections, we are starting a new cluster. And each of those new clusters is like spreading in a new local group. And so we're going to put a guess that it's somewhere like a combination of these two. I don't have a good argument for this. I would like someone to tell me this is right. I don't entirely believe that is right. What I want to say is that, or all I want to say is that if we have the original business as usual scale-free model, we get growth faster than exponential. If we allow people to go about their business but tell them to avoid crowds, we still get exponential growth. We get linear growth if we keep everyone at home, and somewhere in between, which at least physically makes sense, if we allow some amount of breaking of quarantine. Okay, so that's the four things that we're getting out of these four different networks. And I'm going to skip over that picture because, well, no, I won't. So this picture is basically a simulation it's a cartoon simulation starting from day 0 in February sometime for something like Perth. I've tweaked all the parameters so that I get a peak, roughly orders of magnitude, something like what happened in Perth. If you just let things continue to spread, you get this growth here, which is in this model. I'm claiming this is super exponential. I'm not going to show that just yet. I'll show that on the last slide. It's at least exponential though. And these are various levels of of work from home, social distancing. So the different probabilities here are the probability that Thomas gets on his bike and goes for a cycle. Right? So you have a probability of going for, so I've called it here P, here it's P, here it's S. So this is the probability of Thomas going for a cycle, S for cycle. So if he goes for a bike ride, then the number of times that can happen will give you a corresponding probability, this expression, or this fraction of cases where social distancing is not being observed. Right, so from that, you can make a statement, hand-wavy statement saying, well, 80% of people staying at home versus 90 versus 70. And I think it was a couple of groups did this about the time, and there's a couple of pictures published in the Australian that showed this. And interesting thing from my picture is that there's not much difference. And as Thomas blithely pointed out this morning, in another context, my error bars here are bigger than the variation between my predictions. So whilst you could say, yes, if you keep people at home more, it's better, but as soon as you get a few people breaking out, then for the relatively small numbers we have here. We've only got 1,000 odd cases in a population of 2 million. I'm simulating this for 2.1 million people. So it depends on exactly where in that population you are, and that gives you much wider variation in outcome than the variation you would expect, than the variation between the median. So this is median, and this is 90% confidence interval. So the message here is social distancing is important. Exactly how much doesn't matter as long as you do lots of it. Okay, that's kind of a toy example. Now we're going to try and do the same sort of thing and try and quantify the effect that social distancing is having in different states in Australia compared to what we're seeing in terms of actual spread of the disease. So we get a bunch of parameters for the rate of infection, the rate of the quarantine, the latency period, sorry. So the rate of infection, the latency period, and the rate of removal. We're going to impose at some time t star a transition from everyone out and about to social distancing restrictions. So this t star is mid to late March when everyone went home, stayed at home. And so we're doing this here, identifying that value t star in the middle here and creating an ensemble of simulations before t star just to give us a distribution of states on the network, and then looking at the effect going forward of different levels of social distancing and different constraints. And again, wide range of outcomes, median somewhere in the middle, and in every single case, New South Wales is a good one because it actually does what the model says it's going to do for a while. But in every single case, the Australian data basically very quickly falls out of the bottom of the distribution. Right? So the interpretation here is that we're doing physical distancing, work from home, isolation, everything so well that we're actually beating the predictions of the model. Another interpretation, of course, is the model is crap, but I'm going with the first interpretation. We talk about the second interpretation at the end. Same thing for WA, for other states. Tasmania, yes, there was some stuff with cruise ships going on there, so they had their own little second wave coming up here. Now, so just to finish off, we've done all of that, and we've got to the state where I should have replotted these graphs, but the data for up to now is actually now here somewhere. So WA, we've not got very many cases. Everything is, yeah, Thomas, I'll answer that question later. It's not quite, that's not quite exactly how it works. Everything is kind of flattened out. We've got not too many cases. So the question now is, what is the risk associated with, well, primary importance, what's the risk associated with starting first year maths lectures again? What's the risk of letting international students back? What's the risk of going to the football again? So now instead, what we want to think about is a slightly different set of models and a slightly different set of networks. What are the constraints we can put on the system to control any likely future outbreak? So for this, I'm going to consider 4 different versions of the same type of thing. So the work from home model, that's the social distancing one we've already talked about. So that's having a small world network, this torus with some long range connections on it and some rate of those long range connections. We're going to take that same torus and make it an Erdos-Rene graph. It's actually not the configuration model, it's actually Erdos-Rene. And essentially, this is modeling people moving about, connecting with random other people in the city, but not in large groups. Allow gatherings up to some certain size. Well, that's easy. We just take the scale-free network and we truncate it. So we identify nodes that are bigger than degree n, and we just throw away some of the edges. And so now we have gatherings up to 50 people, 100 people, whatever we want. And finally, we're going to make some pretty bold assumptions about the COVID safe app. We're going to assume that, so if an infected person with the app infects someone else with the app, then we can identify that contact. And we're going to assume that we can do that with 100% accuracy in 0 time and remove that link and remove that infected person from further infection. If all of that works 100% effectively, then if a fraction x has got the app, we're removing a fraction x squared of our links from the network. Right? So COVID safe is effectively just depleting the edges in the network in this model. I will skip over this because actually now we're way down here somewhere, but this was an attempt to model based on seeing this number of new infected individuals. We're making an estimate of the number of exposed individuals that have not yet been detected. So on the first day that we see 0 new infected, we're expecting, or we're estimating there's somewhere around 10 to 15 exposed individuals still yet to be identified. I can talk about this later, but I won't because I want to get to the last graph and before I get to 4 o'clock. We can then run these different scenarios again with error. So I've got sick of my wide error bars. I've actually replaced my 90% confidence interval with a 50% confidence interval here, just because the error bars are so huge. But essentially, each of these curves is seeding the population of Perth with 5 infected, 5 exposed, and allowing for different levels of restriction. I won't talk through the details here. I'll get to a slide at the end where I can, and watching what happens from reopening football grounds through to everyone staying at home, staying where they are. You get different outcomes. And the scale here, this is a linear scale of between 100 and 500 infections. Of course, there are, and this relates to Thomas's question, there's a rate of infection and a rate of removal. Change those numbers and nothing else, and I get a different bunch of curves. So this all depends, of course, not entirely unexpected, on the epidemic parameters, but I'm changing them over quite a wide range here. And these parameter values here are not really, as I understand it, are still not very optimistic. These are very pessimistic parameter values. These are the parameter values we use to fit the initial explosive growth on day 1 when everyone did nothing. So, however, what am I going to interpret from this? Well, I'm going to first of all throw away all of my confidence intervals entirely and just show you the medians. So there's lots of reasons why we shouldn't do this, but just for the sake of simplicity of the discussion, the dotted lines are if we have the contact tracing COVID safe app on half of our mobile phones. Right? So each dotted line corresponds to the respective solid line. Excuse me. The black line is allowing football to restart with spectators. The red line is allowing us to go about our business, but no more than 50 people in a room. The number 50 is not important, just truncating it somewhere. The blue line is really saying we don't want people to gather in any sort of large numbers at all, and the green line is staying at home. And so here the scale is logarithmic, and you see the growth plateauing very quickly when we're all staying at home, which is what has happened. You see relatively modest growth if we're careful, and it's fairly well contained. You see exponential growth if you have a limit on the number of people of any large number, larger than 4. And this is what I meant by super exponential. You see this thing growing faster and faster until it gets to the point where you've basically got herd immunity because you've infected, in this case, over half the population. So that's it. That's the end of my talk. I'm just going to finish with one more slide. At some point, I mentioned that paper from 2006 from Hong Kong SARS super spreaders. So this journalist from the Wall Street Journal found that and called me up and asked me some questions. And I said, yes, well, in fact, because I've been talking to David, I've actually done some of this modeling and we're looking at these same sort of things. He asked me some questions, I made some statements. And one of the statements I made is here, and this is probably the funniest part, or the most insightful part of the whole article, as far as I'm concerned, is comments that this person at the bottom of the Wall Street Journal article was basically slagging me off because apparently I didn't get the corner office I wanted. I'll stop there and take any questions.
Great. Oh, that's so interesting, Michael. Thank you for the talk.
And Lyle, I'm really quite happy with my office.
Do we have questions for Michael?
I have a question, if I can.
Yeah, David.
How does the data compare with the first COVID 0.1 data of Hong Kong or other countries?
So you mean the 2003 COVID?
Yeah.
Yeah, so basically Hong Kong was the only place where there was a lot of community transmission for 2003 SARS, apart from China, but we don't know what went on there. So the first thing to be said about the data is the Chinese data from 2020 is a lot better than the data they provided in 2003. There's a lot that can be said about what they're not doing in 2020, but what they did in 2003 was horrendous. I have the daily time series data from reported SARS cases in China from 2003, and essentially it's a flat line with a very large spike and then exponential decay. And what happened was official policy was SARS does not exist in China, so everyone reported 0. At some point after it was widespread in Hong Kong and it was established that it came from China, someone in the government said, stop underreporting SARS. So everyone immediately grossly overreported it, and then there was a recovery from that. So something went on in China, we don't know what it was. Hong Kong was seeded by one person coming from China, infecting a group of others. There was local transmission in Hong Kong, and then there was small outbreaks in other places. People left Hong Kong to go back home to Vancouver or Taiwan or Singapore. But most of these other places, very few cases, and what did occur in other places is really individual. It's individual cases, individual transmission, individual stories. Hong Kong was the only place where there was anything to look at in terms of data. And so that's the...
So the question is, why is the data, why is the model not over predicting or over being over pessimistic about the outbreak?
So there's essentially the models, all of the model predictions are essentially predicting very, very little new infection after the start of control. Right, so all of this, so the worst of the figures, which I haven't shown here, and again, this will make Thomas happy. I don't think there's any that. So the very worst of them, I have predictions where I start from a day here. You can see I'm pointing at Tasmania. I start from the point of control, and then my error bars, one of them is vertical, and one of them is horizontal. Right? So this is cumulative cases. So it's predicting everything that could happen, could happen. But there's the thing that I'm not controlling, which could force these curves down further, is the latency period and the rate of removal. Right? The other thing that is not reflected in this data is importation. I've made a very simple model where the cases I'm getting are local transmissions from other local cases. In a lot of cases in Australia, up to a third of the cases were actually imported on cruise ships or from airplanes or whatever. And so that means I'm overestimating the local transmission in the first place, and so overestimating the envelope of local transmission into the future. And that's almost certainly what's causing the rather spectacular overfitting going forward here. Is that what you're getting at?
Yeah, I was thinking that the initial condition was probably wrong, namely that you have too many hot pockets in your local nodes, and maybe not like a import of the disease through something and just let it Yeah.
So this is actually a really, really good question. I'm assuming that it's just seeded by a few individuals that spread it within the community, but if you have community spread that's not detected or not treated, you're going to have a very different initial pattern moving forward. And so in many places, the US, for example, and many parts of Europe, if not most of Europe, you've imported a large number of cases before doing anything about it. And that's kind of giving you the spread from all over the place before you start. But if you were to believe these network models and actually want to take them seriously, then estimating that initial distribution is critical and really, really, really tricky.
And super exponential growth hasn't been seen yet. It doesn't seem like it's happening.
I would claim it's when you get these bursts of large numbers of cases from the religious festivals or the footballs.
In the US, there's no social distancing and very little restrictions nowadays. So, are we predicting super exponential growth? Or perhaps Brazil is also a worse example.
It would be a spectacular prediction if it turned out to be true. It would be a pretty terrible prediction if it turned out to be true as well. Unfortunately, I think that if the US election goes the way Donald Trump, or the US electioneering goes the way Donald Trump wants it to, you're setting up the conditions for that.
Deborah, if there were questions about the use of the model in working with councils and others like that, I'm happy to.
Okay, great. I think Lyle has a question now, right?
Yes, I was just wondering, Michael, you at the end of your talk, you put up this graph showing something like this, yes, showing what happens under a range of strategies. And these things only go for 150 days. Have you done modelling further out? Because I think one of the things we should be interested in is what are the long-term effects of a thing like this? Is it going to hang around forever? Are these very low-lying curves, the blue one, for example, down towards the bottom, is this thing in fact the beginnings of exponential growth, or are we? I mean, are we going to be all? In 5 years, are we all going to have been infected with this thing? And
yep.
What are the long-range effects?
So the purpose of this picture was really to show if you're in a position like Australia where we have no local cases and we want to return to some sort of normality, but we're going to have a risk of importing cases from somewhere, whether it's from Victoria or from students coming back to campus at the beginning of next year. So this was really a question about whether, under different scenarios of the new normal, what is the outbreak going to look like and what do we have to deal with, contain? So it was really focusing on this kind of detection level here. Right? You want to be able to detect these sorts of 10 to 20 cases and clamp down on it before you get beyond that. Now, the question about long-range future predictions, I guess, unless you follow these black curves and you get to the case of herd immunity, then you are dealing with essentially, I would think, a situation where you're going to have a constant background threshold of tens, hundreds of people coming with the disease and being infected. And I guess this is more of a question which probably requires more detailed modelling, but it's more of a question about how many beds do you need to deal with this continued emergence of cases, and how much do you need to constrain super spreader events to prevent yourself getting beyond this sort of green, red line, blue line here and up to these
Yes,
measurements.
so certainly medium term, these are the important questions. It's just I'm looking at your blue curve there.
Yep.
I'm thinking if we ran this for, I don't know, 4 times as long, or maybe it's not realistic to maybe the model would need to be changed if you were looking at a long time period. But I'm just thinking what you're doing here is appropriate for the emergency and dealing with the emergency, but for planning long term, I mean, it's a different question, really, isn't it? So,
Yeah, it is a different
what
question.
world are we going to be living in?
Yep. And although there's not evidence of it here on this graph, my expectation from my hand wavy arguments earlier is that the blue line would be exponential. It is the start of an exponential growth.
That's the worry. Yes.
And essentially, it's the cold hard fact of disease transmission. If you're going to have anything that looks like a homogeneous mixing of people, then if you exceed the epidemic threshold, you will get exponential growth.
And the long term may be that most people will have had us or died from it.
It's certainly a possibility. I mean, in terms of talking about long-term future, let's not ignore the fact that there's a lot of very smart people working on vaccines and working on improved treatment, and a lot of the fatalities have been due to failures of health systems to cope with numbers. Not all of them, but many of them have been due to too many people overloading health systems.
Right.
So potentially bleak, potentially an important message in terms of the importance of modelling and science and mathematical epidemiology. But I think that it may well mean that we're going to change the way we do certain things to avoid these type of scenarios. Models can do many things, but you're asking it to extrapolate very, very far into the future now.
Yes, just understand that. It's just an interesting question because it will determine how we live. Thanks, Michael.
Yeah, go ahead.
Question. I noticed that in your model, you didn't consider the infectivity of exposed people. And in fact, some if exposed people, individuals are contagious, and when they have symptoms, before they have symptoms, they have the most infectivity. And I think this model may underestimate the spreading of the coronavirus.
Yeah, so I think if I got the main part of the question was about the varying infectivity over time and over individuals, and specifically that people can be highly infectious before they develop symptoms. Is that the right summary?
Yes.
Yeah. So, so definitely there's a lot of things like that which this model does not take care of. This model, epidemiologically, this model is incredibly crude. I've got one rate of infection P, one latency period Q, which is how long before you become infectious or asymptomatic. So that's the period after infection before symptoms, and one removal parameter R to take care of people getting removed from the community either through, or hopefully through treatment and quarantine, but through treatment, quarantine, or recovery or death. And it's only those three numbers that are epidemiologically that are driven by the epidemiology. So there is a lot more that could be done, and I'm basically throwing my hands up and saying, I don't know that, I don't know how to do that, so I'm not doing it. However, on your specific question of people transmitting the disease whilst being asymptomatic, that's a huge factor here that is being overlooked and is driving potentially a lot of what's going on, because it means people are moving about the community. It means they're spreading the disease, not being detected. That essentially it gets back to David's question about seeding the simulation, the initial conditions to the simulation. And if you've got people who are infectious and infecting others widely in the community, then that's changing the initial conditions entirely and potentially making things much worse than what these models are predicting. On a bright note, obviously there's some stuff in the literature where people are saying the complete opposite of that and saying, well, if everyone's getting infected, then we've all had it and we're all immune and it's all okay. That's a plausible story. I don't know whether that's particularly likely.
Well, in Spain, they've done a national survey of what is it called? The antibodies. And they found only 4% of the total population had antibodies, which is a very serious it's very low compared to what they predicted. It's
actually a big concern, and
I don't think that the theory that everyone has been infected is true. It just the
herd immunity is orders of magnitude away, and this kind of gets to Lyle's question as well. People are worried about a second wave, like it's going to be a first wave, a second wave, and then everything's calm. The first wave is infecting, well, in the US you've got 1 million out of 300 million, and already 100,000 dead. Second wave, it's going to be orders of the same magnitude, hopefully, no more. But that's a few million people out of 300 million. That's nowhere near herd immunity. If that's how it plays out, then there's a third wave, a fourth wave, a fifth wave. Then it's going to continue to be something that's a continuing threat. I will say, just as a side note, there was on those kind of different belief systems as to what's going on. This article was kind of curious, mostly because of the 400 and something comments that it generated on the Wall Street Journal, which, apart from ones about my office, tended to revolve around either all these scientists are idiots, they can't tell us anything, I know everything anyway, and everything they're predicting is completely clearly wrong, or exactly the opposite. And there seems to be this belief system that the science is wrong and I know better. I know everyone's had it and everyone's infected and we're all going to be okay. It's only like a flu. It's not as bad as we think it's going to be. And it's really bizarre kind of mental gymnastics that some people seem to be going through to effectively, in their mind, cure the world of the pandemic. Anyway, I'll stop philosophizing. Any actual questions?
Oh, there was a comment from Fabian about if dynamical networks can better model the social structure.
Yeah, so that's also a good question. Because I'm not a great programmer and because I like things simple, I've just used a static network here. My argument for a static network is, well, you're only going to infect so many people before you become removed anyway, so why bother changing the connections? But actually, it's a bit of a dodgy argument, really. We should be looking at dynamic networks, and dynamic networks are going to have a big effect on this. So for example, if you say, I want to limit things to 20 people gatherings, that's one thing. But if, as was suggested in an earlier question, you can be infectious but asymptomatic, you go to your 20-person gathering, you go to another 20-person gathering, and if everyone in those gatherings got infected, that's the same thing as a 400-person gathering. So that's not being modeled by this model, and that could make a huge difference. And obviously, Fabian complicates things pretty quickly too.
I might just add one thing. One aspect of this model in terms of dynamics was that it was very quick to generate and give me useful results that I could use within a few days with a city of 100,000 people. So not as someone building the model, but as someone using results. That to me was really helpful.
Yeah, so this actually connects with conversation that David Pfeffley and I had online before I started doing all of this. And essentially, what is the point of doing? Well, I'm not making a prediction here that's going to tell you what's going to happen. I'm making simulations, and I'm not giving information which you can't get from other models in some way or another. But what it does is it depicts a range of realistic scenarios in a way which people can grasp quickly. And this does actually seem to make a difference. I think KK had a question.
Yeah.
Super spreaders are random from high degree nodes. Yeah, so essentially what I'm saying, a super spreader is, the super spreader events that we see are essentially when the disease infects a high degree node, and therefore that high degree node has a large number of subsequent individuals that it can infect. And so the evidence for this, first of all, is things like the bird flu study that I showed, where we inferred a scale-free distribution. There may be more now. I haven't read the literature recently, but at the time, the only other sort of claims for the scale-free distribution of disease transmission was for sexually transmitted diseases, where, again, you have individuals with a very large number of contacts and many individuals with far fewer contacts. The connection to things like the coronavirus is that we're trying to infer whether this is a likely model for the large outbreaks that we see that have been argued to be linked to things like football games or religious festivals or whatever else. Now, Shanshan's got a question. Yeah, so Shanshan, this is a similar question to the one, was it Richard, I think, asked. This is relating to the infection during incubation period. And of course, essentially what this is doing is it's extending the time in which people can infect others. So in my model, you're exposed, but you're not infectious. Then you become infectious and you can infect others. But as soon as you're infectious and can infect others, there's a probability of you being removed, right? So what's actually happening is, well, it seems what's happening is people are asymptomatic and infectious. So there's kind of a fifth state. After the exposed state, maybe I'll just go to picture. Sorry for that. So after the exposed state, in the exposed state, you've received the virus, but you're not symptomatic and you're not infectious. But then you pass this other state where you are infectious and you are still asymptomatic. So you cannot be removed because you are not going to be diagnosed and you're not yet infectious, and you're not going to recover. But there's some additional period between E and I where you are out and about spreading the disease with impunity, basically. And so you're actually building up many more infectious and exposed individuals in the community who then go and do the same thing again. This is kind of a huge threat in this sort of model, in this sort of epidemic dynamic, because this is something that we don't usually consider in disease models at all.
Great.
Any other questions?
Yeah, I think we don't see any other. Oh, another one from KK.
Yeah. So the time just a week. Yeah. So the super spreader events. So KK's question about whether the super spreader events are going to occur in time in some way, and so essentially the probability of incurring a super spreader event is going to increase if you've got more infected individuals, because there's more chance of finding a highly infectious individual. And there's some funky stuff going on the networks in terms of things like the friendship paradox, which I'll just drop in there but not say anything about. But they can occur at any time if you just happen to find a highly infectious individual. So what you see is essentially that also explains some of the variability, not in these graphs per se, but some of the variability that we see in the growth of the spread in these early stages here, because this sudden jump you see here, and again, this is a median of a distribution. It's not representative of a single trajectory. So some of these trajectories are jumping up much quicker, some of them much later. just whenever they see super spreader events. So essentially, you have random rare events driving the large-scale transmission.
Okay, so do we have another, maybe, yeah?
Oh, perhaps a comment.
Yeah, go ahead.
Michael, I heard you say several times that, or that it's a problem, these people who are infected but asymptomatic and can spread, and we wouldn't know about them. But my understanding is that the PCR test, the one where they stuff the swab down your throat and up your nose and very far, actually can detect whether you have the virus, and hence can catch people who have the virus and would be able to infect other people even though they are not asymptomatic.
Yep, and this could be, so I didn't know half of what you said, Bowen, but I'll believe you. But this could be a very scary future for all of us, where we're going to have to be tested with swabs going up our nose and down our throat to ensure that we're safe to give lectures.
Or at least regular testing every second day or so.
Yeah.
And it takes a day for the test to come back. But so my understanding is the PCR test whether you have the virus. So they would catch you even if you're asymptomatic and before you become infectious. It's a serum test, a blood test, which would say, do you have antibody? Did you have the test? Which are completely useless and to keep the disease down in the population, or to find people fast to quarantine them.
So that's one thing I didn't really talk about here at all, but not the PCR test, because I don't know much about that, but the whole idea of monitoring and regular testing. Of course, if we have to face a future with this thing around for the next 2 to 3 years or whatever, then that's going to be part of daily life as well, as we try to ensure that the community is safe. And
well, I guess one answer is to keep the borders closed and or open it, but put everybody who comes in first for 2 weeks in quarantine.
So what you need to do there, and hopefully this part, well, it is recorded, but hopefully the Vice Chancellor won't be listening. What you need to do here is explain to the Vice Chancellors that this requires regular testing with swabs up your nose and down your throat. And if they want to bring back international students, this is going to be a reality of university life for the foreseeable future.
Yeah, if there's a danger that it is spreading in the community, I rather would like to have the solution that we declare ourselves as being virus-free.
And you just do it at the airport.
Relocate Perth Airport to Rottnest, and anybody who comes in can stay there for 2 weeks first before coming to the mainland.
I knew you were a secret secessionist. I mean, you want to put a hard border with the rest of Australia and keep that there as well, right?
Yeah, we can also have, I mean, in Northam, there's already a quarantine station. We just have to reopen it and everybody stays there for 2 weeks. Yeah.
Yeah, I think for somewhere like WA, there are actually plausible, although maybe uncomfortable solutions like that, which would allow us to function as a state.
At Bourbon, we would be allowed to go diving while we are in quarantine, yeah?
Well, except if you come over from back from overseas, you wouldn't be in quarantine, would you? But yeah, you can go diving, I guess.
But the thing is, if I have to go back home, visit my family, come back, I have to go on to Rottnest quarantine. I want to do diving.
Ah, yes.
Yeah.
Good. Yes.
Jack just posted in the chat, Michael.
Yeah, I saw Jack. Yeah. I want to go and get a beer, isn't it? Beer o'clock yet? I was curious about the impact of mean degree on the network. We changed the mean degree.
Actually, I had the same question, but I was waiting for the part-time transcript.
Yeah, that's a very easy question to answer, and the answer is yes. So the mean degree is, well, okay, there is some complication related to Kirker's question about super spreaders. If you've got a larger degree, you've got more tickets in the lottery of finding a super spreader. But for most of the modeling, mean degree, it's just probability of infection P times mean degree K. So increased mean degree, increasing P. So this is, you've actually hit on something there, Jack, and this is exactly why I'm kind of not worried too much about the P and the R and the Q. I do kind of take care of. I think the P and the R parameter I don't worry too much, because there's not a complete answer there. It depends on the K as well. And that's why you didn't see anywhere in this talk any statement of any reproduction numbers, no R naughts, because it's not just P divided by R. It depends on the degree and the degree distribution as well. But quick answer is yes.
Thank you.
Fit the parameters to reality. That is something that essentially, to make this model really real, you need to get a model, get true data of our contact patterns, right? So how many contacts do we really have, and get true data of the rates of infection of a contact. So I'm kind of defining a contact to be a possibility of transmission. And that's going to depend on the disease. In this case, we know a bit about it, and we know that contact means, apparently, if you're an American, it means being within 6 feet of someone. If you're an Australian, it means 1.5 meters. Whatever the number, there's some magic number which counts as contact or doesn't. And so we need to know how many of those happen. And then we need to know the probability of infection for one of them. And then we need to know the rate of removal, R, which is going to depend on how well we manage things like testing and how diagnosis, and also just the passage of the disease.
So how do you get this data? Like, how do you, like, why do you think it's a good fit? Like,
so I'm saying it's a good fit just from the qualitative dynamics on the data. It's growing in the same way, and so essentially I've got 3 parameters, but 3 parameters is enough, and I haven't done a great job of it, but 3 parameters is enough to tweak it so that my disease spread fits the envelope of the exponential growth, right? So essentially what I've been doing here, and what I hid from you a lot, is in the period up to the point of inflection here, I'm fitting the exponential growth by hand. So I'm changing P and R to make the growth match the pattern that we see. All right. Effectively, what that is doing is exactly the same as what people do when they estimate R naught from infection numbers and then plot curves from that. Now, the part going forward, there's a lot more uncertainty in that, because there's a lot more that we really don't know quite so well as we should. And I would love to get the data from the COVID Safe app, but of course that data apparently doesn't exist.
So I'm sorry to insist here.
Yeah.
It's a bit, so I'm just asking because basically it's like, well, it's hard to model an explosive phenomenon, right? So if you expect your stuff is going to explode, then, well, your initial condition matter, your rates matter, and well, at the end of the day, if you get the parameters wrong, then your trajectory is completely off, like by an order of magnitude. So how do we manage that? What kind of technique can we use to control that effect?
It's really tricky. So one of the problems here is that even with this data that I'm presenting here, a lot of this is post hoc fitting to the data. To determine the rate of infection now is, well, in Australia it's not so difficult, but go to Washington and try and determine R naught at the present moment. That's really complicated. It's complicated by a lot of things I didn't even talk about, but this is where you really need the epidemiological expertise. You really need the statistical sampling, and there's a whole bunch of stuff which I don't know anything about. Berwin probably knows more than me, in terms of trying to estimate these rates of infection from the observed data. And then there's a separate problem of trying to estimate the social contact patterns of people, the social networks. We're trying to do some of that, some stuff I've got working with Thomas Stemler, where that's got his attention, where we're trying to get some mobile phone movement, people movement data from Google, from mobile phones. Not even sure where that's at, Thomas. Do you know anything? Yeah. People tend to not like to have their movements tracked too closely. And it's a bit of a problem for things like this.
Okay. I'm sure Michael is happy to take further questions.
Well, Thomas is going like this, so I think he's heard enough of it.
No, I mean by email, or I mean the seminar will be recorded, so you're welcome to drop in further questions.
And we have a website now.
Yeah. So we have this online website now, and I'm just post this in the chat. So you are welcome to have a look. And next week I will also include this in the email, so you can find previous recorded seminars there. So great. I would like to say thanks everyone for coming. Thanks Michael for the great talk and the discussions afterwards. And I'll see you next week. Have everyone a lovely evening.
And thank you all for all the questions. It was great.
Thank you.
Yeah.
Thank you.
Thank you.
I am going to be rude and disappear because I need to have a pit stop before I get to the pub.
That's okay. See you soon.
See you guys. See you, David.
Thanks a lot, Michael. Yeah, thanks very much, Deborah.
Yeah, that was really nice. Hope to see you soon.
Thank you.